Hi guys, Dr. B here. So we are going to look at the atomic families of the periodic table. In class, we already covered energy level diagrams, electron configuration, full and noble gas, how to draw a Bohr model, etc. So now we're going to look at the different parts of the periodic table. You're not going to have to know all of these families, but we're going to focus on only a handful of them. So all the rows are read from left to right. When you look at the periodic table, each row is called a period. So horizontally, those are periods / rows. All the elements in the period have the same number of atomic orbitals. So as you know, as you go across, like, let's see, like this is the third one. So 3s2, 3p6 going across this way. So you know that they all have the same number of orbitals. Even going from here to here, yes, this is 3d, but they still have 4 orbitals on each side. Around each of the nuclei for these elements. The periodic table has a special name for the vertical columns. Each of them are called groups. So the elements in each group have the same number of electrons in the outer orbital. These are called valence electrons. In a couple of classes I mentioned these, and these electrons are involved in chemical bonds with other elements. For example, nitrogen, which has an atomic number of 7, if you look, it's in the 15th column and it's labeled group 5A or VA, right? So the Roman numeral is for 5, so you'll know that it has 5 valence electrons. So we're going to cover 5 different atomic families, and you need to know these. Apparently, when I was making the slides, I didn't realize that you'll need to know these was typed out twice. I guess I really wanted you to know these. So the first one is the first column except for hydrogen, okay? Hydrogen's not a part of this. These are the alkali metals. Alkali metals have only 1 electron in their valence shell. They're going to become 1+ ions. They react strongly with water and halogens, and they all have the following Lewis dot structure. So a Lewis dot structure is focused on the valence shell, the valence electrons. So for example, for sodium, which is an alkali metal, it only has 1 valence electron, so I would put 1 dot to indicate the Lewis dot structure. So even though there is more than 1 electron in a sodium atom, we're only focused on the valence electrons. So they have only 1 electron in their outer shell. They're 1 electron away from being happy or being full. So when you're that close to having a full shell, you'll want to form a bond with another atom. So alkali metals are shiny, light in weight. They are malleable or bendable, like we talked about, those physical properties. And sometimes you're able to cut it with a dull knife. So because of this, you probably wouldn't want to use alkali metals in coins and all, coin shortage and all that, but in houses and all that. The next one is alkali earth metals. So that's beryllium, magnesium, calcium, strontium, barium, and radium. So alkaline earth metals. So they have 2 valence electrons. They like to become 2+ ions. They're less reactive than alkaline metals. So you may find some of these, like calcium carbonate, in your hard water, like on your shower walls. So the Lewis dot structure is, you put the symbol, whatever it is, so calcium, then you would put 2 dots. So what I mean that they want to become 2+ ions, think about it this way. So these represent electrons, the dots. So in a calcium atom, you have 20 protons and 20 electrons. So if these two, if it was formed in an ionic bond, this is jumping ahead, but if this was in an ionic bond, it will lose these electrons. They will go somewhere else. You have your full shell below that, but because you lose 2 electrons, so 2 minus 2 electrons, you end up with 18 electrons and 20 protons. So you have a 2 plus charge because now you're not neutral anymore. Sometimes they'll form a double bond or a single bond with different types of atoms. So calcium oxide, beryllium fluoride. You see radium on the bottom. Radium used to be used in glow-in-the-dark paints, and it was mixed with something else. You can find them in other things like fireworks, batteries, flash bulbs. Magnesium and calcium are important in physiology, so calcium helps build our bones, and magnesium can be found in chlorophyll molecules. So the next family are the transition metals. This is the D block that we talked about in class when we started talking about the electron configuration. So transition metals, they can have weird charges. So I don't know if you noticed, or some of you did notice on your list, there are a lot of things that have like +2, +4, +7, and so what this is referring to is the how should I put this? Refers to the d electrons. So what I mean is, let's do like with I can't think right now. With iron, how they had the 3d6, so they had those 6d electrons in the third orbit. Some of them will jump up into the outermost one. So it would go up here, for example, and then now you have more electrons in the valence shell for that particular element. Part of this leads to their ability to conduct electricity well. And these different charges, like we talked about, will lead to like iron with 2 plus or iron with 3 plus, etc. Most of them are shiny and have higher melting points. So the Lewis dot structures for these, remember, it's based on your number of valence electrons. So if iron has a 2 plus charge, that means it would lose it has 2 valence electrons on it because these are going to be lost later on. Iron 3 plus would have 3 valence electrons that are going to be stolen later on. That's the general idea. So what makes them so special? Like we said, it's their shells and orbitals. Transition metals are able to put more than 8 electrons potentially in the outermost shell. You also need to remember that these electrons are added to the second to last shells.